Greetings and welcome, friends. Today we are in section 4.5 of our Big Ideas geometry book. We're talking about dilations, which is our first non-rigid transformation that we're talking about. And a dilation is a transformation in which a figure is enlarged or reduced with respect to a fixed point C, called the center of dilation. Other concept is this idea of a scale factor, K, which is the ratio of the lengths of the corresponding sides of the image and the pre-image. All right. A dilation with center of dilation C and scale factor K maps every point P in a figure to point P prime so that the following are true. All right, if my center happened to be the point also that I was dilating, it gets mapped to itself. That makes sense. If P is not the center, then the image of P prime lies on vector CP. All right, so for instance, here's vector CP, and if that kept going, notice that P prime also is going to be collinear with C and P. All right, and the scale factor K is a positive number K such that, and it's the image compared to the pre-image, so it's going to be CP prime compared to CP. All right, so scale factor is going to be image over pre-image. Image over pre-image. So if this was like twice as far, the scale factor would be 2 to 1. Right? It was doubled, which makes sense. If you did it the other way, then you would be saying that the image is a half of that, and that wouldn't make sense. And then check this out, angle measures are preserved. So these angles are congruent to each other. Corresponding angles are going to be congruent. But the side lengths have all been multiplied by the scale factor. So these figures are not congruent, but we'll talk about the idea, I think maybe today or tomorrow, that they are similar to one another, that there is something preserved between them. It's not like it just became any old random triangle after the transformation. When the scale factor K is bigger than 1, the dilation is an enlargement. When K is between 0 and 1, it is a reduction. It does now mention the possibility of a negative scale factor, but we will explore that possibility today as well. All right, here's example 1. All right, and this is not too bad. It says, find the scale factor of the dilation, tell whether or not it's a reduction or enlargement. So this is all about making sure you know which one is the image, right, image, and which one is the pre-image. And my scale factor K is just going to be this total length to the image, 12, over the pre-image 8. And if I reduce that, looks like 4 goes into both of those, into this that many times. So it's a scale factor of 3 to 2. 3 to 2. Or you could imagine this as being like 1.5 times for all the side lengths. Or you could also think of this as a like 50% enlargement. But either way, because this number is bigger than 1, this would be an enlargement. Enlargo. Man, I can't. Why am I enlargement? There we go. Ba 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 ba. All right, over here, this looks pretty similar, but notice that this time this is the image. Okay, so the scale factor K is going to equal 18 to 30. And it makes sense. If it got smaller, that means the smaller number will have to be in the numerator, the larger one in the denominator. And what goes into both of those? Is it just 2? 6. Thank you. Yeah, so 3/5 is the scale factor. So you could imagine this is 60% of the original linear dimensions of that. And because this is a number 0.6, right, is between 0 and 1, then it is a reduction. Right, so really the thing that you're just going to have to remember is what number goes over what number. And that's going to be your challenge. It turns out you can also do dilations on the coordinate plane, and we'll have a convenient way of finding the coordinates. And it's actually, it's super convenient. Coordinate rules for dilations. If you have a point, x comma y, and it's dilated with the center of dilation at the origin, so there's my center of dilation, and the scale factor is k, all right, then literally what you do is you just multiply the x and the y coordinates by k. It's not that bad, right? And whatever this distance was, this distance is k times as much. So if this distance was d, then this would be k times d, all right? It's k times as far away, and then, yeah, this is actually a super convenient outcome for us regarding our points. Let's see, can I snapshot this in one go? Why? Come on, go away, little window. All right, here we are. Here we are. Nope, I pasted it in the wrong window. There we go. Example 2. Man, I'm such a professional. Everyone have a fun snow day yesterday? Oh no, but I wanted to let them know. No, I was thinking of snowshoeing, but I didn't. Snoshing. I did do some spreadsheeting. I did some lesson planning. Did a little bit of Lego Worlds. I have children though, and skiing's expensive, and feeding children is too. They're like, my oldest is 5, so yeah, I'm not really interested in. I'm gonna teach them to have a hatred of skiing, and then when they discover it later, they'll be like, "I'm doing this anyway, Dad," and then I'll be like, "Wah, yeah, on your own money, bam." Didn't know that. Let's see, graph, triangle, abac. Hey, look at this. I conveniently already gave us our original points. You're welcome. And dilate with a scale factor of 2. So that means A prime is just going to be 2 times 2, comma 2 times 1. We'll just do this out for this 1 point. So that's the same as A prime, right, being 4 comma 2. Here, let's make it a different color as well. So A prime is now going to be over 4 up 2. Here's A prime. All right, B prime, man, I'm already changing colors, is going to be double the coordinates for both of these. So that's going to be 8 comma 2. So check this. Over 8 and up 2 is B prime. B prime. And C prime is going to be double the coordinates of point C. So 2 times 4 is 8, and 2 times -1 is -2. And it actually will automatically kind of take care of this all for me. So over 8 down 2. And I'm left with this wonderful triangle like so. There's C prime right there. So they just asked me to graph it. The scale factor was 2. Notice that this distance is doubled to get to A prime. This distance, it was kind of like going down 1 over 4, down, that's actually, yeah, down 1 over 4 from there will actually land me there as well. That distance is doubled overall. That the side lengths have been doubled in size. This was originally 2, and now it's 4, right? That everything's been scale factored up. The only thing that is not doubled is the area. If you could imagine my fitting these triangles in here, you could fit 4 of these like some sort of triforce inside here. That the scale factor was 2 for all of our linear dimensions, including perimeter, but for area, it's the square of the scale factor. So there you go, friends. There you go. Let's do example 3, where we've got a fractional scale factor as well. And man, it looks like I've got to dilate this maybe 83% to fit it on the screen. That looks good. All right, so I've got a quadrilateral Kalaman. Yeah, there we go. And let's see. So K prime, we'll do this proper once. I'm just going to 1/3 those coordinates. So 1/3 of -3, comma, 1/3 of 6. Right, that's just going to become K prime is -1, comma 2. And so K prime is -1 up 2. There's K prime. K prime. K prime. All right, I was like, man, wasn't that like that Kevin Spacey movie where he was an alien in the psych ward? But no, that's K Pax. Classic mistake there. So there's K prime. Notice it's 1/3 of the distance from the origin, and all of these wonderful things. Its coordinates are literally 1/3. L prime is going to be 1/3 of 0, which is 0, 1/3 of 6, which is 2. So that's 0, 2. So there's L prime. N prime is going to be 1/3 of -3 is -1, 1/3 of -3 is -1, left 1, down 1, N prime. And lastly, oh, guys, I missed M. I did it in the wrong order. That's fine. That's fine. I'll just deal with it, guys. 1/3 of 3 is 1. 1/3 of 3 is 1. Over 1, up 1. M prime. And this quadrilateral is similar to the larger quadrilateral. Its dimensions have all linearly been cut down by 1/3. Its angles are congruent. Its perimeter is 1/3, but its area would actually be 1/9. That's right. 9 of these little ones would have fit into the large one. Yeah, or the square of the scale factor for the area. Yep. Let's see. You guys can fall back and do some of those other monitoring progress problems at a different time if you'd like. But let me show you some of the facts about dilations before I do a negative scale factor. It says the following. If you have a scale factor that is negative, it turns out you can view it as a rotation of the figure after a regular dilation by the positive amount. So here's the pre-image. If I was to scale this up, whoop, 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 right like that, I could get this. And if I rotate that, whoop, 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 whoop. Actually, we'd rotate this way. 180 degrees. This would be the scale factor of the negative number. Although I like to, I don't necessarily apply that. Just notice that if I was to scale factor this in this negative direction, that all of these points would have negative or opposited coordinates. Actually, I did that to the wrong one, didn't I? My first red arrow would have landed here. My bad. Right, that it just kind of gets negative dilated is what happens. So you could imagine it as a scale factor, then rotate, but we'll take the shortest route possible because mathematicians are efficiently lazy people. So let's look at example 4. Right, today's lesson, not that bad. Not that bad. Yeah, that's not that much cheese. Oh man, I can't fit it, guys. I've got to scale down. Bam. There we go. Using a negative scale factor. Wow. So for instance, like point G here with a negative scale factor is going to now be down in this quadrant when all is said and done. But let's see. Let's figure out. So f prime could be found by doing -1/2 times -4, comma, -1/2 times -2. Right, this is literally just the super convenient way that this all works out. -1/2 of -4 is +2, and -1/2 of -2 is going to be +1. So that would be f prime. So here's f. F prime is now going to be at over 2 up 1. So notice it's on the opposite side of the origin, and it's half the distance. So this distance here, cut in half, is now that. So here's my f prime. Let's see, g prime. Half of -2 is -1, but now opposite it. Half of 4 is 2, but opposite it. Let's see, so over 1 down 2, G prime. Right, notice it's on the opposite side of the origin, and it's half as far from the origin. And H, yeah. It's nice to have kind of like a lesson where it's not super rigorous in difficulty. You know, sometimes it's just nice. And H is going to be, H prime will be at 1, 1. And notice that this triangle is in fact kind of a rotation of the other one, and it's half the linear dimensions. Yeah. So yeah, you could actually see that this here and here and here and here, those all could fit in there. So that'll give you maybe some amount of buy-in regarding future stuff that we'll do. And guess what? You can apply this to like photos and stuff. With example 5. It's amazing. You guys are gonna be like Photoshop experts or something. So, guys, making your own photo stickers. Your photo is 4x4 and the image is 1.1 by 1.1. What is the scale factor? So I'm going to take these dimensions, 1.1, and divide by, ooh, look at that. That's like definitely like emoji face almost worthy right there, a little text-based. I think so. So let's see, 1.1 over 4, that's the same as 11/40ths, if you wanted to think about it as a scale factor. Now, these were both in inches. What's the scale factor's units going to be in? Trick question here. Scale factors are a ratio, and ratios have no units. And you could think about this as being inches over inches, and that those units cancel each other out. So a ratio has no unit of measure. And then also you can measure your nightmares using scale factors. Yeah, every day. Look at this. Oh, this is horrifying. Absolutely horrifying. You're using a magnifying glass that shows an image of an object 6 times the object's actual size. Yikes! Determine the length of the image of the spider seen in the magnifying glass. So this is, okay, so this is the image that's seen. If the scale factor K was 6, that brought me to this image, right? That means 6 times whatever the original size was, I'll just call that X, would have given me 1.5. And I could divide both sides by 6. All right. And wait a minute. No, my bad. 1.5 centimeters. Let me read this again. No, I was wrong. I was thinking this was the thing that I saw, but that was only because this is how big it looks so big on my screen. I thought this was the magnified image. Well, if I knew the magnified dimension and I was going backwards, this is how I would do it. Yeah. Which is 9. And so the magnified image is going to be 9 centimeters. My apologies. All right, thanks for watching, mis amigos de internet. Adios.